So as you may have noticed, we have just created out of thin air a new function. We don't know much yet about it, and we only know that it solves some, from the first sight, quite a special differential equation. But from now on, we will show how to use this function to actually solve a much broader class of equations. And before turning to this, let us think a bit on properties of this function. And some of these properties can be read directly from the series. For example, it's very easy to figure out what is the behavior of this function for small x. And all of its derivatives can also be understood in a very simple way. But this behavior at small x is obvious from this form, but immediately we appear to have faced with a much more complicated equation. And this question is, what actually is the behavior of this function at large x? And by large, I mean either large positive or large negative. And when faced with this question, we understand that the series is not enough to answer it. Because, for example, let us try to think what happens with the series when x is, for example, large and positive. So as we know that the series does converge, it means that only a finite amount of terms that contribute to it. But say, take x very large. For example, for a moment, let us come back to a simple case of a equal 2, b equal 1, and say x equal 10. Then first terms, so what does the series become? We already have seen that. Etc. And then, although we know that it must eventually converge, we see that term by term, the separate contributions become larger and larger. So, for example, this is of the order of 1. This becomes of the order of 10. And this is already measured by hundreds. This is already measured by thousands. And there's no sign of apparent decay of the absolute values. But we know that this factorial will win sooner or later. And all what we can conclude is that if x is, say, 10, then this value is actually quite large. It can be potentially gigantic because terms grow and grow. And we understand that only term with index 10 or 11 will be the largest one. And later, the decay will start. And this means that the value of this series is actually very large, but it's almost impossible to conclude how exactly large it is from summing the series. And but we can at least understand that it is large and the function is monotonously growing with x. The situation becomes even much worse for x, say, minus 10. And in particular, what happens is that although the terms, the particular terms grow by magnitude, in addition, they oscillate. So and the series becomes something like 1 minus 20 plus 2 or third times 100 minus 3 over 2 times 1000. And it seems almost impossible to sum this series directly. And even less possible to make some quantitative decision about properties of this function. So at this stage, we are facing a problem. And in order to solve this problem, we need to develop an alternative representation of the same function, which does not involve summation of many terms in a series. So in order to construct this representation, let me write this function m in a bit more formal way. So in particular, observe that it can be written in the following form. This is just shorthand for this long writing. And this a and bn are just combinatorial coefficients whose meaning is obvious from this form. But the main achievement in writing this function in this concise form is that we now will try to work on some representation for these combinatorial coefficients, which will be useful in providing alternative representation for m. So in particular, we will need the following important and useful identities. So first of all, let's try to think a bit more on actually what is this ratio and how it can be represented. So recall that this is just nothing but shorthand for the following notation. And a convenient way to represent each of these factors is the following one. So let us, for example, concentrate on AN. If you if you inspect closely this product, you will immediately find out that it is nothing but a ratio of two gamma functions. And indeed, all the terms which are smaller than a in magnitude cancel in this fraction, and all what remains is exactly this product. So in this way, we proceed with the following identity. So finally, this is the first identity which we are going to use. The second one is well known to you by now, beta integral of Euler, which is given by the following expression. This integral, as soon as it converges, which we'll assume, from now on can be written as the following. So first of all, it is nothing but Euler beta function of alpha and beta, but from the other hand, it can be written in terms of gamma functions. So our strategy for dealing with this is the following. So first of all, we express this combinatorial factor as the ratio of gamma functions, and then for this ratio of gamma functions, we make use the beta integral representation, and this will allow us to construct a new representation for M, which is called integral representation, which will be shown to you on the next slide.